So, all right, yeah, let's get right into it. All right, so my name is Tor. I'm the guy on the left. I work for a company called Motional that makes self-driving cars. Specifically, I work on the motion planning team. And so, as you might have guessed, because I'm here, we use C++. And one of the questions that I like to ask when I'm interviewing a candidate is, why would you use C++? Why would a developer or a team use C++? Right? So you get a variety of answers, like it's convenient or it's fast, right? But for me, the reason to use C++ is because it's convenient to write fast code. This is sort of the promise that C++ makes, is that there are these so-called zero-cost abstractions, right? And so, thanks, Daniela. So this talk is ostensibly about copies in C++, but really that's just a vehicle to talk about and to discuss this promise that C++ makes, that it's going to abstract away the details of patterns which are optimal, but are kind of inconvenient to express in C, for example. So the first part of the talk is going to be about sort of the basic types of copies. The second part of the talk is going to be why the entire first part of the talk is wrong. And then the third part of the talk is going to be what we can do about this. All right, so I mentioned that the idea is that we abstract away some of the things that are kind of inconvenient in C, but we can still write optimal code. So let's write some C. Okay, so this is a basic sort of function in C and C++ as well. So when you start a function in C, you have something called the stack. You're somewhere in the stack. You have a stack pointer. When you create these local variables, the C compiler does this really nice thing where it allocates that space for you. And then in this case, it'll allocate that space 4 bytes, and then it'll set that data, right? You can also allocate and then copy data as well. This is called a scalar copy, sort of the first basic type of copy. So we load the data from that other location in memory into a register, and then we store from that register into this other location in memory. Right? And then we, when we return, the C compiler does this nice thing where it just moves the function pointer back, right? So you get this automatically cleaned up local variables. Right? So that is really easy to express. You can also express structures. You can do the same with structures, right? So we've sort of defined the structure. We create one of them as this temporary variable, and then C has this nice syntax where you can use the same equals assignment to assign a structure, right? What will this code do? So for now, we're going to say that this type of copy, the compiler will essentially do this. So it'll essentially do a scalar copy for each of the members. And if those members are themselves structures, it will recurse them and do scalar copies for those, for their members, right? This is completely wrong, but we'll talk about that later. So I mentioned, right, like I claim that it's inconvenient to express some pretty common things in C. And one of those is just basically just a dynamic array, right? Let's call it vector, for instance, right? So we have some pointer to some data that is going to live elsewhere. You don't want to use the stack for everything, right? Maybe you want really like a large amount of data, or maybe you want it to exist not just for like a function lifetime, right? There's lots of reasons. So the first inconvenient thing is that we have to remember to null this out ourselves, right? So we have to do this. This will allocate this on the stack, right? And then when we call some pushback function or something, that can then call malloc. It can allocate that on the heap, for instance. Now we're pointing to some block of memory, and we store the value 33 in there, right? But of course, at the end here, when we return, this is going to move the function pointer back without actually releasing that memory, right? So we've leaked it in a sense. Right? So of course, we need to remember to free this data. Right? So this is already sort of the first sign that this is inconvenient, right? So this sort of pattern is very succinctly expressed in C++. So we can write the same thing just like this, right? And basically all we're going to do here is we're going to tell the compiler, hey, when you allocate that stack space, call a callback function that we can customize on that space. And then at the end, when you're about to deallocate that stack space, then call a callback function on that as well, right? So that beginning callback function, this is kind of nasty code. I borrowed this from a really great presentation about move constructors in Rust. But basically, we allocate this buffer on the stack. And then we're going to call placement new, which is just going to call this function right here, essentially. So this is the constructor. This is the default constructor specifically. And then the compiler knows that we've now initialized this to be of this particular type. So it's safe to just reinterpret this memory to refer to this type, right? So now we can go ahead and use that. And then the compiler is going to do something here at the end. It's going to add in a destructor call, right? And so this is going to defer to, this is going to call free, right, in this case. So it's going to clean up that pointed to memory, right? And that's how we get this really nice code in C++, right? So these zero cost abstractions that let us do this, right? But we want C++ to be a sort of superset of C, right? So we have to support other syntax. Specifically, we have to support this sort of struct assignment, right? This struct copy. So how do we do this, right? One first idea might be, well, could we just trivially copy this, right? What happens if we trivially copy this? So we're gonna create our first vector. Then we're gonna allocate space for the second vector. And then, well, maybe this refers to something on the heap. Let's just copy the value of the pointer over into the new one. But now we have a problem, right? Because both destructors are going to try and free the same data. In addition to the other problem that, well, if we access it from either one of those, they're accessing the same memory, right? So we haven't really done what semantically feels like a copy or a duplication of data. And this is where we get our third copy that we've seen, and this is deep copies. So what the compiler is actually going to do is basically the same thing it did with the other constructor, except it's going to call a type of constructor that takes in the original object. And one thing that's kind of key is, well, because we want this to mimic the C behavior, it's going to take in a constant reference to that original object, right? Yeah, but is this actually the behavior that we always want? In C++11, we decided, no, it's not, right? So here's an example. If we have a vector of vectors, now we have this sort of double layer of indirection on the heap, right? When we initialize this, we initialize this on the stack. It's going to point to some block on the heap, which stores a bunch of more pointers to the heap, essentially, right, in an array. Then we make the first one point to some other block somewhere else on the heap. Now, when we get down here, let's say we've exceeded our capacity. Well, then the way vector is implemented is we need to allocate a new block, and we need to copy the old objects over, right? And if we do this with the sort of recursive copy constructor, right, the deep copy constructor that we saw, then this is unfortunately going to also have to reallocate this block for this first subvector as well, right? But we didn't really want to do this because there was nothing wrong with that original one, right? And you could imagine that you could just have vectors of vectors of vectors of vectors of vectors, and this would just point to some really long chain. We only want to change sort of this first layer in the chain instead of changing the entire chain, instead of copying the whole thing over. Right? And that's where we get the notion of move semantics. We want to shallow copy this. right? So this is kind of what I said the copy constructor for vector sort of looks like. This is extremely hand-wavy pseudocode, so don't write this down. But essentially, we allocate a block of memory for the new vector that we're creating, and then for each of the items, we copy them over, and this is going to use that deep copy constructor, right? So it goes to the next level, it recurses to the next level. So instead, we just want to do this, right? We just want to copy the actual value of the pointer over, like I mentioned. Right? So we'll call this the move constructor. But note, we don't want the destructors to race to get to freeing that memory, right? So we actually have to set the original to null pointer, right? And because of this, well, what kind of reference are we going to take here, right? It needs to be something mutable. Unfortunately, we can't use an L value reference that is just vector and, because by the overload resolution rules, that would bind to the copy constructor, right? Because it could just call this const overload. So this is the curse of like language design. We have to introduce a new type of reference. And so that's called the R value reference. It has 2 ampersands, right? And this is what that move constructor will sort of roughly do, right? And this cuts that chain. It's not going to recurse any deeper with doing copies. Okay, so how do we use this? Well, okay, so here's an example where we copy the data, right? So we create some vector, we allocate some memory on the heap, and we set the value to 33. And then we just use the basic assignment here to call the copy constructor, right? Now, if we want to move this instead, we somehow have to make this of type, vector and, right? And so we can use static cast. And static cast doesn't actually do any instructions. It's just a little way to hack overload resolution into choosing this other overload instead, right? And we have a shorthand for that, which is kind of nice. It's called std move. So this will do that cast for you, and it will choose the overload that you want. All right, and that, I guess, now we have sort of this kind of family tree of copies, right? We have our shallow copies, trivial copies, scalar copies, and moves. And then we have our deep copies that call the copy constructor. And that is, that's my whole talk. Thanks for coming. I'm just kidding. Unfortunately, the reality is not so simple at all. So we need to talk a little bit more about move semantics and some of the intricacies. So move semantics doesn't really play super nicely with some of the other big features that are in C++. So one of those is exceptions, right? C++ has this ability for any function to just throw an error, and that gets automatically propagated upwards, calling destructors as it goes. So here's a simple structure that just wraps, a vector, right? So this will implicitly be movable and copyable, right? But we could also write it like this with, default. This will have the same behavior in this particular case, right? So if we go ahead and use this, this is the same example as earlier where we have sort of the nested vectors. When we get to emplaceback, let's say we've exceeded the capacity and we need to move everything over. This is successfully going to call that move constructor, the behavior that we wanted from earlier, right? And that's right here. But let's see what happens if we just declare this instead of defining it as defaulted. Right? So when we declare this is perfectly legal to do in C++. You declare the function, and you could define it even in a different translation unit. So you just tell the compiler, hey, the linker will take care of this and put in a valid function here. Just pretend you have a function to use. Now, when you get down here to the call to emplaceback, this is unfortunately going to deep copy the vector over. Right? You no longer get that move, even though we have a valid move constructor. Okay? And the reason why is because this struct definition here, this is equivalent to saying this, right? We define, when we do this equals default, this explicit defaulting here, the compiler knows what the definition of that is going to look like because it has to generate it. So it's able to say, I know this isn't going to throw an exception, right? But unfortunately, if you declare this and define it somewhere else, the compiler just has to assume that this could throw an exception. And if this can throw an exception, then we're subject to the exception guarantees. So CPP reference, if you scroll down on any function in CPP reference, you'll see that they usually have a section for exceptions, right? And so for vector, this function has to have no effect. It's called the strong exception guarantee. And so basically any function that has this effect, it can't make use of the move constructors because they modify the original object. So what we're essentially saying here is the original object has to stay constant so that we could potentially rewind to that state and leave the original in a good state. And that's actually wrapped up in a function called move if no except, right? So to clarify S constant, yeah, it do the right thing. So it does whatever, like the compiler can use its own knowledge, right? Thanks.
Right. What I'm getting at is just that if you're saying default, am I right that if you say default equals default there, then it will figure itself out in terms of no exceptness?
Yeah, exactly. You actually don't even need to specify no except or a conditional no except. It just knows, right? So it's kind of nice.
And what if you declare it but then default it in as your definition?
You declare it and then default it. As long as it's defaulted in, like if it's defaulted, that would have to be in the same translation unit, so the compiler would know, right? So
cool.
Yeah.
Thanks.
Yeah, it is.
Sorry to derail.
Yeah, no. Thanks for the question.
Yep.
Yeah. The compiler will complain. The compiler will actually not complain if it can't be no except, I believe. It will just terminate if an exception happens. Yeah, no except is
what I'm
sorry?
saying is that if you have an inline definition of the function that you expect to, that you default it, and you say, well, I expect this to be no except. If it turns out to be no except at compile time, the compiler would error out and say, like, you just told me it's supposed to be no except, but it's not. It's the same with const expr, right? When you default them,
yes,
it's gonna fail if it's not const expr
right
at definition.
Right, if you default it, yeah, that's true. Yeah, so this sort of behavior is wrapped up in this nice little standard library function, move if no except, and it actually basically just, this is the implementation, right? Just sfinase to find what it should do, right? Copy or move. All right, but I mentioned that the original object has to be const. Right, and that kind of brings up a bigger question. Wait, do move semantics not work with const? Oh boy. So yeah, if you have, here's our example again of copies and moves, right? We're going to copy this first one, but we're going to move the second one. If we declare the original vector as const, will this move? Or will it fail to compile? Actually, it will succeed to compile, and it will just silently copy without warning you, right? Without telling you at all. And this has ripple effects through the standard library and your own code bases, right? So just two examples. The first one that I encountered was that shared future. The get function of shared future is a little, it's const. So here's an example. Maybe you have a custom thread pool that uses shared future. And so you're going to return a string from another thread. This is a way to pass a string across thread boundaries. And you're thinking, oh, I'll just pass it in a future and then I'll move it so that it doesn't have to get reallocated. It's just allocated once, and then we just pass the pointer over the thread boundary. Right? So you just move from the result future. Unfortunately, this will deep copy the string. And that is because shared future only returns a const reference. And this is actually not that surprising because I think 90% of the time I've seen user-defined getter functions for user-defined classes. They only have the const reference overload, right? I rarely see people write, move overloads, like R-value reference overloads for this and other non-const overloads, right? But there's actually a much bigger problem with regards to const. And this, I guarantee, is in everybody's code base if you're using vector, right? So this is pretty elegant syntax, right? We want to define a vector of vectors, so we just use these lists like this, right? But what does the syntax actually mean, right? It's how are we able to get this sort of very concise, we just list a bunch of numbers? So this actually uses something called an initializer list. And so this initializer list, it's also on the inner ones, but those aren't really of concern for this problem. And so initializer list of vectors. Okay, well, what is an initializer list? Let's check. Okay, initializer list, it's a proxy object, okay? It provides access, right, to an array of objects of type const t. Oh boy. So this code is essentially equivalent to writing it like this, where we define these as constant vectors, and then we add them to this vector, which implies that they have to be deep copied in, right? So this code has to deep copy the vectors in, even though they're temporaries. They're right here where we don't expect these to live any beyond this, right? Yeah. So this is kind of flabbergasting as an example, but okay. So let's take a step back. Why can't we move from const, right? If you Google this, if you look on Stack Overflow, for instance, you'll get comments like, well, it's a performance issue. It's not a bug, right? Your program is technically correct, even if you copy in this case. Or, well, it's so that generic code can fall back to copy, right? If generic code were to just use move and it didn't compile with non-movable types, then that might not be so great. But I think the real reason is because move semantics are second-class citizens in C++. C++ does not have first-class move semantics. So let me show what I mean by that, right? So this is our example, simplest example of moving one vector into another, right? So this first line, this is going to allocate the data. The second line is just going to copy over data, and it's going to set the original to null pointer. Okay? And then we're going to destroy in reverse order. We're going to destroy the copy first, or the moved value first. And then we're going to destroy the original, right? But this just frees null pointer. This is a no-op. This doesn't do anything, essentially. Let's compare that to the C version from earlier, right? So here's an example of how we might do move semantics in C. It's very manual, right? We have our vector object. We're going to allocate some data on the heap, set the values. And then when we do this line, this is just going to do sort of the trivial copy, right? The struct copy from before. And then we can just make sure to just call free on the new object. And so two things are missing. We haven't set the original to null pointer, and we haven't called another free, right? So in this case, the C++ version, this is not a zero cost abstraction over this. Right? But there is a programming language that does support this kind of move semantics that we're talking about here, and that's Rust. So in Rust, this is kind of the equivalent example. We create a vector with these numbers. This calls malloc. This allocates the data on the heap, and it copies those values in. And then this line right here, by default in Rust, this uses a move. Right? You don't have to specify move. It just by default moves. You have to specify if you want to copy. Right, so this does the trivial copy that we talked about before, but then it calls a special function, which is mem forget. And this is just the compiler like bookkeeping and saying, hey, I can just ignore this object, right? This is now uninitialized memory for all intents and purposes. I can just not call the destructor. And so then it's only going to call the destructor of the new object. Right? And I think this is pretty cool because, well, yeah, I think this is pretty cool because it's obviously less work. But there's also something pretty interesting, which is that the original vector doesn't need to be mutable. You can totally move from const. There's no problem with moving from const in this model, right? So I guess to compare these two approaches, like the move semantics approach from C++, it mutates the object, the original object, at runtime. We need some way to tell the object that it has been moved from so that it can not destroy the original resources. But in the Rust model, which you might call this trivial relocation, this mutates the original type, right? It mutates the internal state of the compiler at that line of code, so that subsequent lines of code, the compiler knows if that has been moved from, right? And so now that's just a single trivial copy. Right? Okay, but I keep talking about like trivial copies, struct copies. Why do we actually care? What's great about trivial copies? Right? So initially I put up this code on the screen and I said it was completely wrong. So let's dig into that, right? So the compiler is a little bit smarter than just doing this. It's not actually going to scalar copy over every field. So I've got Compiler Explorer embedded here. So I've got two functions to compare here. This first copy function, this is doing the implicit copy that we're going to ask the compiler to just figure it out. And then the other one is going to do the explicit copy. Now, if we look at the assembly, we already see that there's definitely a difference between the assembly here. What's going on? In the explicit copy example, well, we've got a, let's see, we got a load in a store, load store, and this is going to use the size of the int, size of the double, and then size of the character itself here. But in this version, it's managed to optimize it to something else. It's doing different loads and stores. So it's kind of hard to just parse this assembly. So I think it's more useful to look at the LLVM internal representation. Right? And so if we expand this, we can immediately see that there's a difference here. So in the explicit copy, right, load, store, and these are the types that we expect, I32, double, I8. But in the other case, it's calling some intrinsic called memcopy. So what is memcopy? So this is the actual source code of memcopy. It's pretty simple. At least this is from libgcc. You can view it on GitHub. We've got a link here. It just takes in some void star of input data, right? So just in C, this is sort of how you just say it's a blob of data. Sorry, my dog wants to be let out. Oops. Dog, come back in. Right, so this just takes in sort of pointers to blobs of data, and then it just reinterprets them as arrays of bytes, right? So this might seem like it's slower because bytes are sort of small, very small types, so it would be very expensive to copy every single byte. But the reason that we care, the reason that this is nice, is because now we can do coalescing. Right, so let's look at this example again. And this time, let's look at the generated assembly. So we can see here that this is doing a load and store using keyword pointers. Right, so quad word pointers. But I've had to explicitly disable SSE because this is on by default. So if we turn on SSE, we can see that this is actually able to do this using fewer loads and stores by using vector registers, right? So in this case, it was able to turn 2 loads and stores from quad words into a single load store using the XMM word. And these are 128-bit registers. right? And if we go ahead and make this an even bigger type, if we just say, okay, this is now like an array of 10 doubles, you can see we've got a bunch of these. But if we go ahead and turn on AVX, or like AVX2, this is now able to use the YMM word registers, right? And so this is 256 bits. And so it's able to do bulk copies, right? And what's cool about this is that this doesn't just happen with single objects. We could do the same optimization for arrays of objects because they're laid out contiguously in memory, right? So if we have a vector of this type S that we just showed, which is a trivially copyable type, then this call to resize, this is going to default construct a bunch of S's. It's going to default construct 4 S's. When we resize it to 8, it has to copy over those 4 into the new block of memory, right? So we allocate these two, and then we copy it over. This is going to use memcopy, right? So it's pretty cool. Now we're memcopying across this boundary the full block of 4 objects at once, right? So you can coalesce across that. So because of this, we really like bulk memcopy. So we definitely want to use this wherever possible. And that kind of the logical conclusion of this is like, well, wait a second. Moves, as we saw them in Rust, are actually this much simpler operation called a relocation, which is just a trivial copy, right? So is there some way that we can get this behavior in C++, right? Because currently we have to iterate over. We have to say for each element, move it. Make sure to set the original to null pointer. Then you're going to call all the destructors of the original. Right? We don't need to be doing all that work. And so that brings us to like the proposal 1144 P1144 from Arthur O'Dwyer. This isn't a trivially relocatable talk though, so definitely go watch his videos on YouTube about this. It's a really great explanation. But yeah, this will allow us to do this for certain types, right? Like vector is trivially relocatable. Unique pointer is probably the canonical case of this, right? Because it's basically just a pointer with the compiler tracking ownership and lifetimes, right? But actually, this applies to basically any type that doesn't have self-references, right? Okay, let's move on from moves though, because most of the time you actually didn't even want to move. Like you really probably should be using move as sparingly as possible. And so what do we mean by that? Well, so far we've only talked within a single function. We haven't talked about function boundaries. Like what happens at the function boundaries? What happens in this example? How many copies are in this example? Right? Like maybe this creates a copy, right? If we have this function, it returns a vector by value. Maybe this gets copied into here. Or maybe now that we know about move semantics, maybe we know it gets moved because this is a temporary. It's about to go out of its lifetime anyway, so you might as well just move it in. It turns out it's a secret third thing. Functions in C++ have a secret argument. They actually get rewritten by the compiler kind of like this. This part is extremely hand-wavy on the code, by the way. This is very, very pseudocode. But they sort of get rewritten to have this slot, right, for returns. And then the caller of the function can just allocate that memory on the stack, pass in the address of that return memory, and then just reinterpret it to be a vector, right? Because this function, kind of like a constructor, has initialized that to be a vector. The compiler knows this is now a vector vince. And this is called guaranteed copy elision. This is one of the forms. This is guaranteed since C++ 17, so hopefully everybody out there, it's guaranteed for you. But what actually happens inside of the function, right? So let's say we wrote our function like this. What would this get rewritten to by the compiler? Well, the compiler is going to rewrite this probably like this. So in this case, we have the return slot. We might as well just construct this array of 1, 2, 3, this vector, in the return slot directly. We don't have any need for this temporary variable, right? And once we've done that, we can just assume that this memory, we'll pretend that this is temp. And so we can just, anything we did to temp, we'll just do to that memory, right? So actually, there's no copies in this example, right? There's no copies and there's no moves, right? And this one above is called the named return value optimization. And unfortunately, both of these are very easy to break. They're extremely fragile, right? So once again, something that move semantics doesn't play nice with is the return value optimization. If maybe you decided you were going to get clever, and if you're returning a temp by value, you think, well, I could just move this out, then I won't copy, right? Maybe you don't know about RVO. Well, the return type is vector of int, right? And RVO only applies if the thing that you're returning is the type of the return. So in this case, it actually says, well, you're going to have this temporary variable temp, and then you're going to have to move it into the return slot. So you're going to call the move constructor on the return slot to initialize that memory. Right? So you've actually broken RVO by trying to be clever here. Wouldn't it be great if we could have this syntax in C++, right? If we could just return multiple things. Unfortunately, we can't. We have multiple returns at home. They look like this. I see this code a lot. But unfortunately, this doesn't work how you would expect with RVO, right? If we had true multiple returns, then maybe we could just RVO each of those multiple returns, right? We could just construct temp1 in the first return slot and temp2 in the second return slot. But in this case, the return value is a pair, right? It's this nested object. Those vectors have to physically live next to each other in the return slot. And so we have to copy construct them in here. So in this case, you should actually move these, right? Because they won't get automatically moved for you. What about a slightly different case? Right? So in this case, we have two different vectors, but we're just going to return one of them conditionally. This is not able to do RVO, unfortunately, because depending on some runtime condition, you might be returning a physically different object. So the compiler doesn't know which one of these it can construct in place. And so we can't do RVO here. But just to really confuse things more, we have something called automatic move. So this, you would think this gets expanded something like this, right? Where you copy this into the return slot. That's actually not what happens. Instead, the compiler inserts the calls to move here for you. Yeah, this is very confusing. It happens sometimes. Yeah. Okay, so our family tree of copies actually probably looks something like this. So we have what you might call like rebinding, right? We're just binding a variable to something else, right? This is where we use return value optimization and initialization from a temporary, which is actually just a different form of return value optimization. On the copy side, when we're actually trying to copy data around, we have our shallow copies, which we can further subdivide into like coalescing shallow copies, right? Trivial relocations, trivial copies, and scalar copies. And then we have like the weaker form of shallow copies, moves, automatic moves, and then throwing moves. I don't know. Sometimes, they could be a move, it could be a copy, right? And then we've got, move from constant and our copy constructors. Okay. Let's get to probably the more important part, which is what can we do about this? So I'll break this up into two things. The first one is you've got a latency crisis in your system and you want to figure out where these copies are happening. Well, there's a couple of creative ways that you can do this, right? So let's say you got this class, it's called please don't copy. Right. One thing you can just do is kind of the nuclear approach. You can just say, no, this type is not copyable. You cannot copy this type. If you're going to do this, though, you're probably going to be faced with a ton of compilation errors if this type is used all over your stack. So this might not be the best option. So something else you can do is just mark it as deprecated. This doesn't change anything about the semantics of your object. Your type, it still has exactly the same type traits as before, except that you get this fun deprecated declaration warning, right? Then you can just downgrade this from an error to a warning at the command line. That's kind of fun. Still kind of noisy, kind of challenging. So I got this other tip from C++ Weekly. You can just mark it as explicit. Right? If you mark your copy constructor as explicit, then users have to write out this very ugly code here anytime they want to copy it. They can't just say equals my type. Downside with this is that it's entirely possible that within certain functions, they do this explicit copying. And so you just won't catch those with this, right? But I'm kind of a visual person, so my favorite approach was to use Perfetto. So if you have like tracing supported in your system, then you can just add traces to the copy constructor of some base type. You also have to make sure to default the other member functions, including the default constructor, as well as like the move constructor, right? But once you've done this, you can just derive from this in however many types you want, and you will just get little markings in your Perfetto trace plot, right, your hair graph, that tell you exactly when copies happened. And so there's a nice way to do it at runtime. Okay, but you should probably just be shaking your head to all of this, because really we want to shift all this left. Get it? We want to shift left. Okay. Your first line of defense are compiler warnings, right? Your compiler, it can save you from a lot of this headache right away. So use them. There's a couple good ones right off the top of my head. Clang has -w move. GCC has some move options as well. You can also use large by value copy. This is not really related to the things I talked about, but sometimes if you pass in a large, trivially copyable object, it would still be faster to pass it by const reference, right? So this can find cases like that. But the things that your compiler can't catch, Clang tidy mostly can, right? So Clang tidy is great. If you look at the list of checks, it's gotten really large. They've released a bunch of new ones actually in the latest version of Clang. So if you just go in here and you just start typing like move, you'll find, let's see, so here's moving from const. You can catch moving from const. You can catch cases where you broke automatic moves. You can catch cases where you don't have no except on the move constructor, right? Yeah. So like a lot of the things that we've talked about so far, a lot of the pitfalls are actually very easy to catch with Clang tidy. And if a check doesn't exist, oh, it's so easy. You could just create your own check. They have this great page about getting involved. Okay, I'm gonna do something a little ambitious, and I'm just gonna develop a Clang tidy check really quick. It's not a Clang tidy talk, but let's just write a quick check. Okay, so you clone LVM.
At this point, you've solved it, so let's go.
Yeah. Okay. So you clone LVM, right? You go into the Clang tools extra folder, right? And then they got this nice little Python function that you run, Python script, right? So we're going to add a performance check, and we're going to catch the cases of vector initializer lists. Okay. So the next thing you want to do is come up with a minimal example, put it into Compiler Explorer, and open up Clang query. Right, so let's use this as our example. Right, and then if you put this into Compiler Explorer and you use Clang query, you can write things like match cxx construct expr. There's a whole page on what these expressions mean, but it's so easy to just like play with this in Compiler Explorer. And so if we type this, we get a ton of results, way too many results, right? We don't just want all constructors. We want to narrow it down a little. So we'll do constructors that use initializer lists specifically. Right? And so that narrows it down to just the ones that we want. But we don't want to catch all initializer lists. We actually only want initializer lists where the type is std vector, right? Where we're constructing std vector. And this is it. You just take this and you copy paste it into the clang tidy check for the matcher, and then you just write some very, very pretty fancy diagnostic message in the other function, and you're done. That's your own clang tidy check, right? So you just go ahead and compile it, and now you have your own clang tidy check that checks for vector initializer list. Okay, so some takeaways. The first takeaway would be, don't copy your data. Like, just like put the data in one place and just leave it there, right? I think object-oriented, so C++ supports like some form of object orientation. And this kind of causes us sometimes to fall into this trap of thinking, well, everything needs to be a doer, or a this factory, or a that consumer, right? And each of these things needs to have ownership of the data and things like this. But as much as possible, if you can think about C++ as like C, but it just allocates for you, or it just maintains invariance for you, and design your code like that, you will just get better performance out of it. So llama.cpp, for example, I'm pretty sure they just memory map the weights into the program when it starts up. That's it, you know? They don't copy big objects around all the time. They just refer back to that sort of region in memory that contains the weights. And then use simple types. This is especially true when we, like with C++ 26, we're entering the age of trivial relocation, right? If you're storing vectors of types, those types should be as simple as possible. Try not to customize stuff unless you're writing like very basic, like low-level types. Try to just use standard library types. Yeah. And then, yeah, trace your programs. Like, keep benchmarks running in CI so that if somebody introduces a copy like this that's catastrophic, then it gets caught. It gets caught early. And otherwise, you can always use Perfetto and trace your program and look at this visually. You can just see so quickly where these hot loops are happening with copies. Right, and then, of course, use compiler warnings and linters. We just talked about that. Make heavy use of clang tidy. Write your own clang tidy checks. Fork clang tidy for your company specifically. I think it's a great idea. Okay, it's kind of unsatisfying though of a note to end on. You know, I feel like we're missing some things here, right? I guess we're getting trivial relocation, but it still feels like we should have like true move semantics in C++. If you're interested in this, definitely check out Sean Baxter and his work with Circle. He's writing a borrow checker for C++. That is, yeah, it's a crazy project. I also feel like it would be cool to have multiple returns. I would really love to see people just stop returning pairs and tuples. Even returning named structs, it still kind of beats RVO like this. True multiple returns, it would be a really cool feature. And I can't help but feel like there's some tool that is like, we're right there, and we should have, right? Maybe some combination of being able to grep and clang tidy, and maybe to run checks from JSON files instead of having to recompile LLVM. Anyway, that's my talk. Thank you everybody for coming. I hope you learned something or had fun at least. I had a lot of fun making this.
All right. 1 second. We have a bunch of questions. So thank you, Tor, so much. This was very fun, at least for me. Really appreciate you putting together. I am sold about clang tidy. I don't know about others, so we'll get into it. So Yanis, doesn't guaranteed copy illusion work correctly with structured bindings?
That is a great question. I need to read about that.
Well, we can do a follow-up. I can
Yeah.
post on the meetup.
Yeah, I will say I didn't want to put something up there that I wasn't absolutely sure about. So I did write that example in Compiler Explorer, and I did get those destructors called for the types inside. So they definitely didn't get constructed in place inside of the function, unfortunately.
Cyan is asking, would make tuple help with RVO? I don't think so, right?
Unfortunately not. Make tuple just existed before CTAD. Make tuple was a way to deduce the arguments from the function call for the type to construct. So actually, I would recommend not even using make tuple anymore if you have CTAD.
Ben over here has found our next topic that Tor will cover, which is Clang Tidy intro.
Oh no!
So thank you, Ben.
Actually, there was actually though on the Clang Tidy, there was a really great talk at CPPCon about Clang Tidy. Yeah. So if you go on the CPPCon YouTube,
well,
there's
we want it live. We need it
amazing
live.
talk.
We need it live. We need it live. So well, you're committed now. Yanis, shame on the compiler. Shame on the compiler in general. I think that's a general statement.
No, I think if it can inline functions, then probably it could solve this. I didn't even talk about inlining, right? I barely know anything about that whole world.
Cyan has hand up, I believe. Cyan,
yeah, go ahead. All right, maybe not.
Tor, okay, Daniele, we can link the Clang Tidy talk. Tor, if you can send me the talk, I can.
Yeah, let me just find it.
I can make a bundle with everything. Oh,
sorry.
O3 will probably inline things, but unless you have LTO, that won't help across the translation units.
Here we go, Kristen Shaker. This is a great talk.
I wonder, also how many, clearly you can't probably share that, but I would be curious to know how many people do run benchmarks on the CI, like you said.
Yeah.
I know we don't. we're trying to, but
we're getting there.
Yeah, we're getting there. It's something that it's kind of, it's a lost art, I guess, but it's very useful. Like you're saying, like if you're knowing that if you're about to push like a major regression, it's better that you get stopped before you ruin everything else.
Yep.
All right. Any other questions?
I sent the video in the chat, by the way.
Awesome.
I also sent the video about move constructors in Rust by Miguel Young. Great talk.
Search CI for benchmarks are useless. Yanni, what do you mean?
If you have someone that basically, if you have like a CI, you have too many users running on it. Benchmarks need isolation.
You mean you need,
try to do like benchmarks on GitHub Actions and see what happens.
Yeah, don't do that.
No, that's part of the questions that we're trying to answer now. We're trying to evaluate if bare metal in AWS can give us what we're needing. Otherwise, we're gonna go for dedicated hardware. But no, you can't do it.
You can have your own private runner, right? And you can basically control it.
Right. Yeah, the idea is just like serverless is not a great idea for benchmarks, right? If you just have a sort of your self-hosted solution, that's usually
we have a question from Dipanjan. What was the design choice behind not allowing move from initializer?
Right. That is a great topic, and I think that there is the phd.dev article about that.
Okay.
So, yeah, a lot of ink has been spilled about that topic. So,
awesome.
Yeah.
Ben, they aren't deterministic, so what? Throw a dashboard. I mean, the truth is somewhere in between. I think when I managed to crack that code for emotional, for reliable CI benchmarks for C++, I think that will be my talk, my talk topic.
Right.
All right. Any other questions for Tor? Just for everyone, we're at the hour. I have one more thing on my agenda. I have kind of apropos of the subject for Tor. I have this book by Jason Turner, who was I referred a couple of times in the talk. It is about copy references. It's a puzzler book. So I have a little spin the wheel type of thing. So if we don't have any other questions, we can see who gets a book and we can call the night. So I'll give a couple more seconds. Going once, going twice. Any other questions? If not, Tor, awesome job, sir. Thank you so much. I will be posting the video. I made a Google account for the C++ meetup, so I will be I'll try to upload it on YouTube. Otherwise, we'll see. We'll see how it'll go there. So let me spin the wheel here. So the reason that I had the RSVP folks, and it may have been kind of annoying for you, it's so that I know how many people kind of RSVP'd here, so I can kind of do this. So just to see that everything is, I'm not favoring anyone. I have my the spreadsheet on the side here. Expert number, what? 46. Give me 1 second. 46. We got Cyan, Samantha. Do we have Cyan here? We do? If not,
No.
oh, Cyan, you won the book. I'll reach out to you. I'll reach out to you through the meetup to get your address, so I can send the physical copy. I can't email it to you.
Thank you so much. Yeah, Tom, great.
All right, no, thank you everyone for joining. And yeah, like I said, we'll try to keep this going. If anyone has a topic that you would like to, take the time, make a presentation, share with everyone, please message me. You can find us on the Slack or on the meetup. I have a Google form that I'll try to be circulating. We are looking for presenters, and I'm trying to make this more of in-person type of event going forward. So yeah, thank you all for joining and spending an hour with us this evening. Tor, again, thank you so much.
Thank you, and thank you to the whole group for having me.
Absolutely, thank you. Bye-bye.
Did it.
1 second, I need to terminate the recording first.